I have given you a homework to find the reactive modes of water molecule. This is water, you all know it very well. Now the total number of modes of motion will be 3n. It is triatomic molecule, so it will be 3 into 3 equals to 9. Now this water molecule is a non-linear molecule. It contains a symmetry axis, rotational symmetry axis C2. Now because it is non-linear, it will have all the 3 rotational modes. So rotational modes will be 3. Transitional mode will be 3 because the center of mass can move in 3 directions. So what will be the number of vibrational modes? It will be 3n minus 6 in case of any non-linear molecule. So it is 9 minus 6 equals to 3. For CO2, we have found that the number of vibrational modes was 4 because it was linear. Now what are these 3 vibrational modes? These are, the first one is symmetric stretching. Second is bending. Third one is anti-symmetric stretching or asymmetric stretching. Now our intention is to find whether the modes are infrared active or not. So for this we have to find whether the modes associate oscillation in dipole moment or not. If it associates oscillation in dipole moment, it will be IR active. If not, then it will be IR inactive, as I have discussed in the previous videos. Now first I will deal with the symmetric one. This is the equilibrium position. Expansion will be on both the bonds. Again the equilibrium condition will be back. Then there will be contraction on both the bonds. Finally, the equilibrium condition will be regained. Now we have to find the dipole moment. Here we have del plus, here we have del plus. So the center of the positive charge will be here. And here it will be del minus, so the center of negative charge will be here. So we will get a dipole moment along this direction from positive to negative. What happens in this elongated case? Here will be the center of the positive charge and here will be the center of the negative charge within the oxygen nucleus. Now see, distance increases between the negative and the positive charge. So the dipole moment will increase. So this will be like this. Again it will be in the equilibrium state. Now contraction occurs, so the center comes here and the negative center is here. So distance decreases, so the dipole moment will decrease. Again it will come back to the original position. corresponding to the equilibrium state. So you see there is an oscillation in the dipole moment and it lies along the rotational axis of symmetry. Now it is symbolized as nu1, and because it is along the symmetry axis, it is termed as parallel. Now if we try to plot the oscillation in dipole moment, it will be like this. Here we will have the dipole moment. Now it is increasing, so we will get a point here. It is again coming back. Now it is decreasing, but still have a magnitude. Again it is coming back to the original position. So see, there is an oscillation in the dipole moment. The oscillation is ugly because of my bad drawing. Not the case that it is not smooth. It will be smooth. Now since we have an oscillation in the dipole moment, it will be IR active. So the symmetric vibration of water is IR active. Now the second case, which is bending. This is the equilibrium configuration. Bond angle will increase from that demanded by the hybridization. Then it will come back again. Now the bond angle will decrease. Again it will come back to complete one oscillation. Here the dipole moment will be like this. Now this center rises upward. It comes here when the bond angle increases. So the dipole moment will be less in this case. It will again come back to the equilibrium value. Here the center comes downwards. So the distance increases and we have an increased dipole moment. Now again the equilibrium value. Now in case of bending, we see the oscillation in dipole moment occurs also along the rotational axis of symmetry. So it is symbolized as nu2 and it is also parallel. The order is given nu1, nu2 because of symmetry. It is symmetric and the symmetric stretching is also symmetric. Now the third case is anti-symmetric or asymmetric, hence it is named as nu3. To observe the oscillation, let us plot. We will plot here. The value will decrease. Again it will come back. It will come here. Again it will come here. So you see and oscillation. So it will also be IR active. Now the third case, that is asymmetric. It is symbolized as nu3 and is observed across the rotational axis of symmetry. We will start from the equilibrium configuration. See, this one will contract and this bond will elongate. Again the equilibrium configuration will be attained, then this bond will elongate this one will contract, and then the equilibrium configuration will be again attained to complete the oscillation process. Here it will be as before. Now the center of the positive charge lies here. In this case, it will come to this position. Now the center of the negative charge is here, so the dipole moment will be like this, will act in this direction. It will be like this. Again, the center will come here. You take the mean position. Here it is the negative charge, so the dipole moment will act along this direction. And again it will be like this. Now if you look across the rotational axis of symmetry, then you will see the projection will vary. It will have projection 0, it will have non-zero projection, so there will be oscillation in dipole moment in case of asymmetric vibration also. So this mode will also be IR active. So unlike CO2, here in case of water, all the three vibrational modes are IR active, since all the three vibrational modes are associated with the oscillation in dipole moment. Now what are the positions of these three vibrational modes in IR spectroscopy? It is found that the symmetric stretching appears around 3657 centimeter inverse. The bending mode appears around 1595 centimeter inverse. And the antisymmetric stretching appears around 3756 centimeter inverse. So these are the positions of the three vibrational modes in infrared spectroscopy. Now one question that may arise in this case is that the symmetric and the antisymmetric stretching positions are far compared to the bending. Now this is because the difference in strength of the vibrational modes. Now vibrational modes will be associated with a frequency, and it can be expressed as 1 by 2 pi root over k by mu. This is the classical vibrational frequency. Now more the bond strength, more will be the frequency. So one can easily claim that the symmetric stretching and the antisymmetric stretching are associated with stronger vibrational modes. Now what is the reason behind this strength? This is because you can easily see that in case of symmetric stretching, it elongates and compresses, and in case of asymmetric the same thing happens. Only difference is that it occurs simultaneously in one case and it occurs alternatively in another case. But both the types of vibrations include displacement against the nuclear force. So when this elongates, this have to perform work against the attraction of nucleus. And when it compresses, this have to perform work against the repulsive force of nucleus. So this happens in case of symmetric and asymmetric. But in case of bending, the work is not have to be performed against the nucleus. It is against the hybridization. So hybridization is demanding a bond angle equivalent to 104.5 degree. So you are increasing that bond angle and decreasing that bond angle. Not that you are decreasing or increasing the bond length. So you are not performing any work against the nucleus. So in this case, the restoring force is less, the bond strength is less, hence the vibrational frequency is less. So that is the reason behind the lower position of the bending vibrational spectra. Now I am giving you a homework between symmetric and antisymmetric. You can easily observe that antisymmetric stretching is associated with a higher vibrational frequency. Why? This you have to explain. Post it in the comment section.